We're live now. Yeah. Hi everyone. Welcome to Vimal DS Mysuru meetup. And it's a masterclass session on attention models and transformers. And about Vimal DS Mysuru, we are a not-for-profit organization. We have chapters across the world and across many cities in India. And we conduct a lot of workshops to help women and gender minorities. We help women and gender minorities in machine learning and data science, give them a platform for to come up, present their work, and to learn from others' work. This is what we do. We have events every week, and so we are also expanding our core team. So if you're interested in volunteering, anchoring, if you're interested in participating in the core, being in the part of core team of MLJS, we are currently the third biggest. We started in February, and we are currently the third biggest community in India. And in short time of 3-4 months, we are around 1,700 members long. If you're part of the core team, do reach out to me in Twitter. My Twitter handle is urengaraju, and we also have a meetup page for Vimal DS. And if you're interested in volunteering, I'll put a email ID in the meetup page. You can reach out to this person. We'll onboard you in. And we also have a community partners for this event. And if you're not for if you're the community in India, and if you wish to collaborate with us, we have events every week. So if you wish to collaborate with us, you can reach out to us. And for this event, we have a couple of community partners. One is Co-Learning Lounge and Applied Singularity, and Co-Learning Lounge has got amazing free data science resources. You can check out their YouTube channel and website. And Applied Singularity has got app which gives you, it's a free app. It gives you a lot of data science resources for you to get started if you're an absolute beginner. And without much delay, today's first session is going to be on attention models. And so the first speaker for the session is Sriranjani. Sriranjani is an alumni of IIT Madras, and she also is the Google developer expert in machine learning. Her expertise lies in natural language processing. Without further delay, I'll hand over the session to Sriranjani to take it. Yeah, Sriranjani, you are in the stream. Your screen is visible. Go ahead.
Hello everyone, are you able to hear me?
We are able to hear you. Yeah, you're audible.
Okay. Yeah. Okay. Just a minute.
Yeah, your screen is gone.
Yeah, 1 minute. Is it visible now?
No, it's not visible again. Can you share again?
Okay. Yeah, 1 minute. I shared it, but it was not. Is it visible now?
Yeah, I've added to the stream and it's visible now. You're audible.
Okay. Yes. Good. So thank you, Usha, and thank you, Usha, for introducing me. Thanks everyone for attending, Sunday late evening presentation. I'm Sriranjani Ramakrishnan. As she mentioned, that I'm a Google developer expert in machine learning. And also prior to that, I finished my master's in IIT Madras, and where we have, worked on multiple range of problems with respect to speech recognition. And after that, I was working in research lab Convent Research Labs, and which was formerly called as Xerox Research Labs, where we had to work on problems which is starting from machine learning, deep learning, natural language processing, speech recognition, etc. So I have a couple of papers as well as patents which is published in these areas. And Google Developer Expert is a wonderful opportunity which I got to be part of the network as well as the group. And it is quite interesting to learn from the peers as well as share my knowledge to the community. And I'm also the organizer for TensorFlow user community in Hyderabad. And yes, so the area of research, area of interest lies in natural language processing, as Usha mentioned, speech recognition, deep learning, etc. Um, 1 minute.
Yeah, your screen has gone.
Yeah,
Yeah,
so I have
I've added
something.
you to the screen now. Your screen is
Uh,
visible.
yeah, yes, is it visible? The next slide?
Yeah, it is visible now.
Okay, now. Okay, thank you. So without much delay, let's go to the talk today. So today we have a very interesting and hot topic of attention models. In today's talk, what I'll be doing is that we will be talking about attention models and what motivated us to start with attention models. And the attention models, which is quite famous in the area of natural language processing, especially with neural machine translation, and how it has evolved in this particular area and is being currently used in multiple applications. So we will be seeing the inside and out of attention models. Now, let's go with the basics of how language models started. So, language models are the most important part of the natural language processing, because language is nothing but a sequence of text and words, and how we model language form the basis of the natural language processing. So, statistical language models started in long back in 1900s or before that. How we what we do is that you try to model the language, which is a sequence of words, as a statistical language model by estimating its probability. So basically, if you're given a sentence, suppose the dog is running, then how are you going to make a probabilistic distribution out of it? And that forms the basis of a statistical language model. So for this particular example, we can see that we can see that the dog is running. You can see that the word dog, the, and then dog is going to depend on the, and is going to depend on the and dog, etc. So the whole model itself will be depending on the previous words or its context. So language model, what it does is it just helps in differentiating between two acoustically sounding similar phrases, and it and to differentiate the two phrases, and which is sounding grammatically correct or the most probable one. Say for example, in this example we can see that recognized speech and recognized speech. In this, we can always say that recognized speech is most probable compared to recognized speech. So how are we going to build this particular model from the basis of the language model? Now, language model can be formed using multiple ways. So the most popular way is ngram, and then you have maximum entropy models. Nowadays we have neural network language model, etc. So language models not only help to form a probabilistic model out of it, but also used to predict the next word in the sentence. So for example, given the four words, if I want to produce the fifth word, so what would be the next probable word, right? So that is the major application, one of the major part of language model. The other one is that you can also try to generate text in many tasks. So what I meant by generating text is that you can select a word which is based on the scene sequence, like say w1 to w4, and then how can you try to add sample it based on some sampling methods, and then you try to add this word to the sequence and looping it again and again to generate text. So this generating text in many tasks has multiple applications, like speech recognition, machine translation, image captioning, spelling correction, text summarization, etc. So the language models with respect to the statistical part, it was forming the basis for a long time, until neural network language model became quite popular in the recent years. So neural network language model are quite popular, mainly because it addresses the data sparsity issue, which was caused in the classical statistical language models, and also the it allows large context sizes. So that helped in achieving way better results with respect to neural language models. And currently neural language model is the most popular language models. For the neural language models, we use neural network architectures like recurrent neural networks, long short-term memory (LSTM), gated recurrent unit (GRU) based architectures. So, to give a example of how neural language model works, you can say that, say for example, if my sentence is going to be, Tom likes beer. And in that case, what happens is that you're going to attach a start token as well as a end token with the sentence, and you're going to, take each of the word in at each timestamp, and then you have a hidden state which can be unrolled in time at each time points, and then you're going to produce the output, right? So that is the general architecture of a RNN means recurrent neural network model. So here you can see that, similar to the example which we saw, neural language model also, that the probability of Tom given the start token, probability of likes given the start token, and Tom, etc., till the end of sentence, we will be calculating, and that will be my final language model. And this is the output of each of the time step which you'll be getting. So the whole language model is learned using back propagation through time, where you calculate the cost and then you're going to back propagate it till the end, and then you're just going to update the weights. So now here, what you're going to do at each time step, as I said earlier, that input the previous word and predict the probability of the next word. So here you're going to see the in terms of equation how you're going to take the xi, which is the next word, and it's going to depend on the previous context of the words. Now, let's go to conditional language models. So, what is meant by conditional language model? Conditional language model are that the same probabilities, but which will be assigned to sequence of words given some conditioning context. So, say for example, in this equation, we can see that p of y given x. So, this is going to be my next word, but I'm not going to just depend on the previous words alone, but also adding some context for it. So this adding some conditioning context makes a problem quite interesting, because if I'm going to consider the input X, suppose any author, specific author, then my text output is going to be the document written by that particular author, or a sentence which is in French, then the output is going to be its specific English translation, or an image which you pass as input, the text description of that particular image, right? We can see now itself that you have multiple tasks and its application, because we add the conditioning to it, and the conditioning makes the task in the application quite interesting as well as challenging. So to train the conditional language model, we need the paired samples of the input X as well as W, and also large amount of data is needed for tasks like machine translation, summarization, speech recognition, caption recognition, etc., caption generation, etc. So it is quite important that these models are much more efficient because of its applicability as well as its usage in wide areas. So how are we evaluating these models? So usually the language models are being evaluated using perplexity, but not all times perplexity can be easy to calculate or estimate. So comparing the models most likely output to human generated expected output using task specific evaluation metrics also becomes important. So any specific task like blue scores, which is used for neural machine translation, WER for speech recognition, MIT or ROG scores. All these are very task specific scores they evaluate the language models on. Now, let's go to the encoder decoder architecture, where I want to make the problem little bit more interesting by considering that I want to learn a function that maps the input X into some fixed size vector and then use a language model to decode that vector into sequence of words. So what I mean to say is that we know that we already have a language model which can predict, which can actually generate text, which can generate a sequence of words. And before that, if I'm going to add some encoding of an image or another encoder of a text itself or a sequence of text, then what happens to it, right? So this problem is quite interesting. Now, as this name suggests, this particular architecture, you have a encoder, as well as a decoder. So and this model is also called as a sequence to sequence model. We will be seeing little bit more in detail about the encoder decoder architecture now. Here you can see that I can just take an image and encode it to some intermediate representation and then pass it on to the language model, which is the decoder, and you will just get the caption out of it. Or I can just pass on any for machine translation task. I can pass on the translation, say for this example, a German translator, and then you are going to encode it and represent it into some encoded in between representation, and then you're going to pass it on as a decoder, pass it on as input to the decoder, and then you're going to get the output in the output as a sequence of text. So this we ask two important questions when we are going to model this encoder decoder architecture, right? So the first is, how are we going to encode the input X into some fixed size vector C, and how do we condition the C in the decoding model, right? So when you ask this question, we are just coming up with some basic representation, saying that okay, so I have this fixed size C vector. I use any kind of embedding of this particular input X, and then multiply with some weight matrix to get the represent embedded representation here. And then you have the normal recurrent neural network decoder, where you're going to take the hidden representation and the embeddings. Along with that, the main thing is I'm just also going to append or add this source sentence representation which I got it from the encoder, and then pass it on to the activation network, and then get the output similar to the general RNN model of how we are going to train it or predict it. So that is what you will be seeing in the encoder decoder architecture. So to see it in visual form, you can see that you're going to have a sentence a token, the same example of Tom likes beer, and you can see that similar to the previous RNN neural network language model, you can see that here the only extra step is going to be this S, which is the encoder representation which has come from source, and then you're also passing it as input to every time step. That will be seen like this in terms of the chain rule of probability for the language model, where you're going to have S at every step. Now, in order to decode, we generally what we will do is that we are going to get the most probable output, and which is given by argmax at W, which is probability of W given X, where you're going to sum over all the time instances and all the words. Now, here, this generally, it's quite expensive. So what we do is that we go for a greedy search, but compared to greedy search, better approximation would be a beam search, where you have a beam size of B, where you try to keep track of top B hypothesis. So where you're going to see here B is equal to 2, and suppose if in German, if I'm going to have beer trinke ish, then what happens is that for each of the token, I'm going to generate two hypotheses because the beam width is 2, and going to keep the best one. So here I is the best one, and for I again you're going to generate 2, which is the drink you're going to keep. Similarly, for drink again you're going to keep the 2 and then beer. So totally when you're going to backtrack it, you're going to say the output as I drink beer, which is the German translation, English translation for this German input which you're passed as input. So not only RNN, definitely we know that RNN has the issue of vanishing as well as exploding gradient, where the if the sentence is quite long, then the gradients try to vanish or explode, and because of the long duration of the values when you're going to back propagate it, and because of that we have LSTM as well as GRU architectures. So, Sutskever and his group have, produced a similar language model for using LSTM. So, this LSTM encoder decoder architecture, what they have tried to achieve to improve the blue scores is that they are trying to read the input sequence backwards. So, these are some of the tricks they use, like not only the forward, but if you're going to read the input sequence backwards, then you are able to achieve better scores. And then also they used ensemble of independently trained models, and then they used beam search. So all these provided smaller improvements of blue scores, but not quite a major one. So uh, this is one step ahead of from the RNN encoder decoded architecture with respect to LSTM. So to see together as a neural machine translation system, as how we saw now, that you're going to have an encoder RNN, and where you're going to have the source sentence as the input, and you're going to provide initial you're going to take a embedding or the representation of the whole sequence of sentences into a one vector representation, and we are going to pass this as initialization to the language model itself, which is a conditional language model, and which is conditioned on this particular encoding of the source sentence. And then you're going to produce the output in the target sentence. So that is the neural machine translation system, which is using the encoder decoder architecture. So, what are the challenges in neural machine translation systems? The challenges are you have out of vocabulary words. How am I going to include it? Or you're going to have a domain mismatch between the trained data as well as the test data. Then you're going to have to maintain the context over longer text, because if my text is going to be quite long, or it's going to be multiple paragraphs, then am I able to translate it properly? And then as I said earlier, that you need pair languages. So if any one of the pair language is low resource, will I be able to still train my model properly and get the output out of it? And we have if I'm going to have biases in the training data, gender biases and other social and geographical biases, how my model is going to get trained to produce the output in the translation, etc. So these are quite challenging points for any neural machine translation system. But the most important with respect to the technical architecture is the vector bottleneck problem, which we will be seeing in the sequence to sequence model. So, what is vector bottleneck problem? Vector bottleneck problem is that, as we saw earlier, that for in encoder decoder architecture, what you're actually doing is that you're taking the whole encoder RNN and encoding the complete source information into a single vector, which you're going to initialize it to the whole language model, which is the decoder RNN. Then it is a overload for this particular overload of information. So it is more like an information bottleneck, because you expect the whole sentence, source sentence information be presented in this one fixed size vector. So that is the vector bottleneck problem. And because of this fixed size vector problem, we might not get the best model output always with respect to the encoder as well as the decoder architecture. So even though we have the gradients, which has come long way to travel, like even LSTMs have the issue of forgetting if it's going to be too long a sentence. And so just changing LSTM or GRU with respect to from RNN is not going to help us with respect to this particular problem. Also, we know that the sentences are of different sizes, and but finally we are encoding all the information into a finite length vector of some fixed size. So that is kind of restrictive. So in order to solve all these problems, the best solution you can think of for solving this vector bottleneck problem is that why should I go for a vector? I can go for a matrix. So what we can do is that we can represent the source as well as target sentence as a matrix. That's quite an improvement from a vector fixed size modeling. And here what we will be doing is that we will be we will be having fixed number of rows, but we will have the column sizes, which is the number of columns is going to depend on the number of words which we will be having. So this particular sentence as matrices with bidirectional RNN was proposed by Bahadanu and his group, and it is quite and it's one of the widely used matrix representation from then. So here you're going to have, as I said earlier, each column is going to be for a word, and this whole matrix is called F matrix, which is going to have the forward representation encoding as well as backward RNN represent encoding, and then you're going to concat it together and just form this particular matrix. Okay, so that is one way of viewing or solving the vector bottleneck problem. Now that we got this matrix, now our possibilities of changing and improving the model on top of it is quite interesting. So this leads to the motivation of forming attention models, where now we have the matrix F, which is the sentence encoding of the whole source, and now we need to generate the output from it. So Bahadanu and Luong concurrently proposed, using attention for translating from these matrix encoded sentences. So why you call attention is because at each time step we want the model to attend to able to attend to different specific words in the source sentence, like how humans we will focus on. So they are just say that it is actually attending to one specific, or two or three specific words, and that's why the name attention got into. Now, what we will be doing is that in attention models, you're going to generate the output sentence again word by word using a RNN, and at each position, you're going to have RNN will be receiving two inputs. Okay, so the first input is going to be the vector embedding of the previously generated output, as well as the encoding view of the input matrix. So this is the one which we have generated it, which is the F matrix, and this is from the previous time point of the RNN itself. So we are going to take these two things, and you're going to append it together and pass it on for the model. And how are we going to get a fixed size vector that changes over time from a matrix? So for that, again, Bahadanu proposed that you're going to do a weighted sum of the columns. Like basically, you're going to see some weights for each of the columns in the matrix, which is going to correspond to a words, and how important they are at each current time step. So it is basically a matrix vector product, which is the matrix F, which is the source encoding, as well as the AT, which is the weighting of the input column at each time step, which is called as the attention. So to just get a visual representation of what I have just explained till now, so this is the whole source sequence embedding, and you're going to get this attention, which is the weighted value for each of the column, and you're going to pass on this multiplied with this. You're going to get as some C2 context vector, and then pass it on as input to the decoder at every time step. So the history of these attention points will be just maintained in this attention history. So to get another, glorified view of this attention model, like the whole model problem itself, which is sequence to sequence with attention, we can see that this source sequence, you're going to have this encoder RNN, and this is the start token of the decoder itself, which is represented in green. And what we do is that we are going to get the attention scores, as I mentioned. So for this particular vector, you're going to multiply in dot product and get the attention scores at every time point. So once we get the attention scores at every time point for the source sentence, what we will be doing is that we will be, taking the softmax and to turn it into a distribution. Here you can see that this particular distribution, which is going to be the weighted sum of these encoder hidden states, and that is going to be the attention output. So this here in this example, we can see that this particular word here, it got the highest attention distribution, which means that the output of this particular decoder RNN at this time point is going to be mostly focused or attended towards this particular word, which is ill, and which is going to come from this encoder RNA. So what we do is that we are going to concatenate the attention output as well as the decoder hidden state to produce the output as before, and that is going to produce he. So we are going to repeat the same step for each of the time points, and we could see that the attention scores and the distribution is varying for different decoder output. So here you can see that the hit word is going to be mostly from me. So then the output of it's going to be me. And similarly for the last one with a pi. So to see attention models in terms of equations, we can see that we have the encoder hidden states, which is H1 to Hn, and we have the decoder hidden states, which is Sp. So this H1 to Hn, which is represented as red ones here, and the green ones is represented as St. And this you then you're going to get the attention scores, which is et, which is given by the dot product between matrix and vector product between the hidden states as well as the hidden state of this decoder. And this whole et attention scores is going to be also called as attention energy. So it's just e, but this is the matrix which I was talking about, which is f, where you're going to just concatenate together to form the matrix X, which is F, which is formed with all these H stacked together. Then we will be taking softmax to get the distribution for it, and then you're going to take the weighted sum of the encoder states to get the attention output. And after that, you're concatenating the attention scores as well as the decoder hidden states to get the input as the context vector, and this context vector will be passed on and proceeded towards learning using a non-attention sequence to sequence model in a general RNN framework. So we can see multiple variants with respect to the attention model production. So we can call these H1 to Hn as values to see in a more generalized form, and this decoder hidden state as a query. And you can see that h1 to hn are going to be in dimension 1, and the decoder hidden state in dimension 2. So always attention modeling involves the computation of attention scores, but there are multiple ways to to do the attention scores, and then you get the attention distribution out of it, and also the attention output, which will be the weighted sum values of these for every hidden states, encoder hidden states. So in Luong, he proposed a basic dot product version of attention, where you're going to take the decoder hidden state and the encoder hidden state that we saw earlier, and also he added a weight matrix with that, and then made another version of it, which is multiplicative attention. Bahadanu has mentioned a more non-linear version of it, where he was passing this through a tanh function, separately weighing the separately multiplying the encoder as well as decoder hidden states using weight matrix W1 and W2, which was learned, and then passing it to tanh function, and then again another v matrix, v vector, which is going to be a weight vector out of it. So this is the additive attention. So all these are different variants of the attentions, and to see that in a generalized form, we can say that attention can be modeled for any encoder hidden states and decoder hidden state representation, and then you're going to get the weighted sum values for it, and you're going to get these values to focus or see that where the attention have gone through for every decoder step. So attention models have significantly improved the blue scores of neural machine translation system, because it focuses on certain part of the source during every step in decoding, and also it provides some interpretability, because you get the distribution, and in each distribution, distribution values in each of the time steps, you are able to get the focus of it provides the information on where the decoder is actually getting focused. So you can just see that as we saw earlier, this ill, the focus mainly was on he, so you're going to get a darker more value here. Similarly for entree, you have with a pie, etc. So the network actually learned the alignment itself, and we don't have to explicitly model anything specifically for with respect to alignment, and that is one good advantage of attention models. So to generalize it, attention model is not only, even though it started for neural machine translation systems, and it improved over there, and people tried to use multiple techniques to improve the encoder decoder architecture. It can be seen as a more general deep learning technique, where given any set of vector values, and as well as a vector query, you can try to see that attention is a technique to compute the weighted sum of values dependent on that particular query. So basically the query which is attending to the values. So here in this particular example of encoder decoder architecture, we saw that each decoder hidden state will be a query which is attending to all encoder hidden state, which is the values. But you can the intuitive understanding is that the weighted sum is the selected summary of information you're able to get in the values, where the query is going to determine where the value has to focus on. So that's what, which values to focus on, that's what you're able to get from the attention. So we have seen a text or natural language example, as we already seen that it is quite a general technique for any representation of a query in a different dimension, and depending on the other values in another dimension, it can be used for various modalities, and people have tried quite extensively. So in computer vision, image captioning example application, you can see that input image of a bird flying over a body of water. What you will be doing is that you're going to encode using some form, right? And then apply it to a RNN or any conditional language model or a decoder. So here, yeah, people have tried using convolutional feature extraction in front as an encoder, and then have used the decoder for RNN or LSTM. So here they have used LSTM, and then you just got the sequence of words. Similarly, for speech, but here the interesting part is you can see that in this particular image, women is throwing a frisbee in the park. uh, so for decoding the word frisbee, you can see that actually the attention is visual attention has been there in near the pixels of frisbee, and also a dog standing on the hardwood floor. The dog is being actually highlighted during the decoding of this particular word. So that's how it is used for visual attention. Similarly, for speech recognition, you can take the audio as input, the spectrogram, which the features are being extracted, and you can see that the output, which is the translation of into text, the alignment information of which phoneme or the character is being there with respect to at what time or millisecond in the audio samples has been aligned using the attention models, and it is quite interesting to see its application in various other modalities also. So apart from that, you have multiple categories where hard and soft alignment is hard alignment is something where it selects only one patch of image to attend, and soft alignment is you're learning the weights over all patches. And using this motivation, Luong and his group has proposed global versus local attention, where global attention is using all the encoder, all the hidden states of the encoder when you're computing the context vector, whereas local attention is choosing only one particular position in the source sentence, which is more localized. As we can see that in global attention, because you're using all hidden states of the encoder, you will be having a computationally expensive process because of each of the words calculation. But in local attention, what you do is that you try to first fix a position in the source sentence, and within that position, you're going to see the words, window of words, which will be chosen, the model attends to. And there is this concept of self attention, which is intra attention of relating different position of the same input sentence, where you're going to give the input as well as the output at the same sentences, and see how which word the focus or the attention has gone into. Suppose if chasing is the current word we are focusing on, we are decoding, then in that case, I'm going to see where its focus was in the previous words, which is being focused on FBI and is. Similarly, for chasing is the word which is being focused on. So basically, this gives us the idea of correlation between the current word and the previous part of the sentence and how it is being used. So Last, but not least, we want to know the computation cost and the time for attention models, because it's very important with respect to deep learning models, how much runtime it takes and how much memory it uses, so that we can use it for multiple applications and applications and reduce the cost. So here we can see that the computational cost, usually for general sequential models, depends on the number of connections, which is the number of add or multiply operations for the forward or the backward pass, the number of time steps, which is the number of copies of the hidden units to store the back propagation. How many number of copies of hidden units you're going to store when you're calculating for back propagation through time, number of sequential operations, and maximum path length across time, which is the shortest path length between the first encoder as well as the last decoder output. So considering all these values between RNN and RNN with attention models, you can see that attention models provide constant path length compared to RNN. And given that the models, attention models, are time consuming, because you need to calculate the trainable weights for each decoder's time step for getting the context vector, and also it is hard to parallelize. We don't know like which time point to where we can parallelize when you are stacking multiple RNNs in a deep layer form with multiple hidden units. So that parallelization part is hard, as well as calculating the trainable weights is hard. So that's one disadvantage of attention models. Even though you have this disadvantage, attention models are quite popular, and it has provided a lot of improvements in various applications, including neural machine translation, image captioning, speech recognition, and other applications. So to solve this issue of cost and time complexity, the transformer models was proposed in 2017. And our next session speaker, Dipanjan, is going to talk in deep about the transformer models and its importance in the upcoming session. So to summarize, we saw that how language models have been used in natural language processing. Then how the language models have been, overtaken by neural language model because of its advantages, and the encoder decoder architecture itself, where the neural language models have been used. And you had the attention models, which is the another variation or the technique on top of the encoder decoder architecture, mainly to solve the vector bottleneck problem. And we saw how attention models itself provided improvement in different task in application, mainly because of the calculation of the context vector with from the source encoder embeddings, and how you're forming the weighted combination of it. And we also saw multiple variants of attention models with its time complexity of the attention models in the end. So that's all for today. These are the resources which have been taken, and if you have any questions, I'll be going over the questions and try to answer some of them, because we have very less time. And before taking questions, I'd like to thank Usha, as well as women in data science and machine learning group for inviting me today for the talk. And it is it's quite interesting to share knowledge and also to learn from the community. And please connect and follow me in the social media.
Yeah, hi, Sriranjani. You have
Hello.
so does yeah, hi. Does RNN decoding suffer from vanishing gradient problem here as well? This is by Vivek. Yeah.
Yeah, yes, here also, but we will be overtaking that with respect to LSTM and bidirectional RNN. So mostly, I think they will be solving it. So here, if you're going to ask separately for attention models, I think no, because you're shortcutting with the encoder representation, and then they can just take it as such. Yeah.
Yeah. So there's two more questions. Like, is self-attention calculation costly? By Suresh. Yeah.
Self attention, yeah, self attention calculation. I Okay, I'm not very sure about self attention calculation, but I think because if you are going to use a similar architecture of using encoder representation for each of the time step, then yes, it is going to be the same calculation for the cost. I mean, it
Uh,
doesn't matter whether it is the same sentence or a multiple target sentence.
so there's another question by Anubhav. In the decoder stage, we have three inputs for the decoder RNN. Encoder hidden states to give attention vector, decoder hidden state, and previous decoder output. Is it correct? I mean,
Yeah.
he's just confirming what you have said.
Okay. So
Okay. Yeah. So there's last question is there's a person who's an NLP enthusiast and he has asked, he knows NLP basics. He wants to study RNN, sequence to sequence, and transformer in detail. So if there is any suggestion by you for any courses or books which you would recommend.
okay, so courses, I think definitely Stanford course CS 224N is very good, and also Cambridge Deep Learning for Natural Language Processing is very good. CMU's also is good. Books, I think definitely Deep Learning by Yan and Yan. So that book is good, and also all social media with blogs and other papers you can go through.
Yeah. There's a final question is by Subhash. How LSTM overcome vanishing gradient problem?
So I think it's LSTM overcome the vanishing gradient problem because of the memory cell and the gate which is having it. So it's basically with respect to the architecture itself. So if you see the architecture difference between the RNN as well as LSTM, RNN does not have a inherent memory which is attached to it, but LSTM have the input read write and forget gate. Based on that cell states, you're able to overcome it by focusing only on the cells which is needed to focus on in while doing back propagation.
Yeah. So, see then, we have covered all the doubts.
Okay.
So, if there are any more doubts, you can reach out to Sriranjani, and I mean, what would be the right channel to reach out to you, Sriranjani?
Oh yeah, I have not mentioned. Sorry. So you can definitely connect with me LinkedIn and also in Twitter. It's Shriran underscore Ramkrish, RAM KRISH, SRIRAN underscore RAMKRISH. So you can just always
Kiran
find me, and
underscore
also
Krish, right?
no, Shriran underscore Ramkrish. Yeah,
Ram Krish.
I can
Okay.
I can yeah, yeah.
Yeah, I've Sriran and hyphen Ramkrish is a Twitter handle. You can follow her, catch up with her in Twitter and in LinkedIn. In LinkedIn is Sriranjani Ramakrishnan. You can catch up with her in LinkedIn, or if you want to like have further questions and things. Sriranjani, there's a
Yes.
lot of positive feedback from your session. People have put the comments in the comment section. You can check that out too. Thank you so much for
Definitely.
joining us
Yeah.
on a Sunday night and delivering a great session. We are looking forward to hosting you again in Wimbledon. Thank you so
Yeah.
much, and yeah,
Yeah. Thanks all. You've been a great audience, and thanks Usha for hosting the session. And yeah, it is quite informative as well as useful for me also to share my knowledge with other people and the community. Thank you.
yeah. Thank you. Dipanjan, can you share your screen?
Hey, can you hear me?
Yeah, I can hear you.
Okay, great. Hang on.
So you're in the screen, yeah.
Let me know if you can see my screen.
Yeah, your screen is visible now.
Okay, good.
Yeah, about Dipanjan, this is a masterclass session on transformers. Dipanjan is Google developer expert on in machine learning, and he also has a lot of achievements which he will be sharing with you shortly. Over to Dipanjan. Best wishes.
Hi, thanks a lot everyone for spending your Sunday. Usha has promised I can go over 1 hour, but I'll try to keep it within an hour. And yeah, today's session will be on the focus will be on transformers in the context of natural language processing. I'll be covering some high level concepts. We'll look at some examples of transformer based architectures, and also I'll try to go into some of the internals with regard to a standard transformer model, and we'll look at some hands-on tutorials at the end of towards the end of the session to see how we can use transformers in the context of popular applications like text classification and also multitask natural language processing. This is the brief agenda. We'll go through a brief introduction where I'll be just talking about myself briefly. We'll give a brief around transfer learning because the whole context of transformers is in the context of transfer learning. So it's good to know what it is all about and why transformers have become so popular. We'll talk about deep transfer learning for natural language processing briefly. We'll go into the deep learning architecture fundamentals so that you can understand the next steps, because the transformer model by itself is a pretty complex architecture. So the idea here is to understand the basic building blocks as well as the motivation which led to transformers. I think Sriranjani in the previous session has already covered a fair bit of it, so it'll be easier for me. And once we cover the motivation behind why we need transformers, we'll go into the essential concepts of transformers, and we'll try to unbox this transformer architecture as to what are the key components inside this model. And once we cover that, we'll look at the popular classification hierarchy of different types of transformer models. We'll cover BERT and distal BERT to an extent, and then we'll move on to the hands-on tutorials. So, a brief about me. I'm a data science lead currently at Applied Materials. I'm also an author. I've published several books on machine learning, deep learning, natural language processing, and even transfer learning for that matter. So, feel free to check it out. And also, I advise and also mentor for edtech startups like Springboard. And I'm also a Google developer expert in machine learning. So since we always get a lot of requests of where's the code and where's the slides, this is the link. Maybe someone can ping it in the chat also, but you will get all the code examples as well as the slide deck. So I would recommend you to listen to the session. No need to like sit and take down notes or try to take snapshots because everything will be available. I'll just pause here for a few seconds before I move on. Okay, let's get started. So, a brief about transfer learning. The idea of transfer learning here is basically the capability to utilize prior knowledge, which we learn from prior tasks, and try to apply it to new and novel tasks. So, in the context of human behavior, it's like if you know how to ride a motorbike, it's easier to learn how to ride a car. If you know how to play classic piano, you can easily learn how to play jazz piano. If you know math and stats, it will be easier to learn machine learning. So, no doubts about that. Now, considering a conceptual overview, so traditional machine learning or traditional deep learning is very isolated in nature, often known as the single task learning, where each and every data set and each and every model is trained in isolation. So if we want to train, let's say, a new model on a new task, we will be training from scratch. We won't be leveraging any prior knowledge from, let's say, the model which was built to solve task number one. But in transfer learning, the whole idea is, can we build a model potentially on a data set where there is a lot of data, and can we use some kind of representations from that model when we are trying to solve this new task? So this is where, instead of trying to build a new model from scratch in isolation, we try to leverage some of the prior learnings from the previous model. And that is where, if we have problems like less data and so on, the model can still perform better given the right circumstances, given the right distributions with regard to the features and the response variables. And we will look at this small data problem when we do the hands-on session on text classification towards the end of this session. And this is a brief about transfer learning. Sebastian Ruder's blog pretty much covers it in detail. So the idea here, or the main objective of transfer learning, is to learn the target conditional probability distribution, P of yt given xt in dt, where dt is the target domain, given that we have gained enough knowledge from the source domain and the source task, where ds is not equal to dt and ts is not equal to dt. So the whole idea here is, can we learn some kind of generic representations which we can still use in the new task, and maybe we can use it directly or we can fine tune it, as we will learn even in the context of transformers later on, where we fine tune a transformer model which was pre-trained to solve our own specific tasks. So let's talk about deep transfer learning in the context of natural language processing. So there are two main stages here. One is known as the pre-training, and the other part is known as the fine-tuning or the adaptation. So this is also known as sequential transfer learning, which has led to some of the biggest improvements so far in the field of natural language processing. So the pre-training is often also known as like the language modeling step, where we try to solve some generic tasks instead of solving a specific task, like, let's say, text classification. So that can include like ingesting large corpus or large corpora of data into a model so that it can learn representations, relationships, sequences between words, and the right kind of embeddings or representations. And there are various types of models, as you can see here, which can be pre-trained. And it is in the order of, you can say, the way it has come in chronologically, where we started off with word to vec, Stanford came out with glove, then there were skip thought vectors, InfoCent, then we came up with Elmo, and then we had ULM Fit, GPT BERT, then there is Transformer XL, and you know all the variants of BERT with regard to Distal BERT, Albert, so on and so forth. So the whole idea is, once these models are pre-trained on a large amount of data, we basically fine-tune it and adapt it to our specific tasks, like question answering, named entity recognition, classification, language translation, so on and so forth. So this is where it gives you a more summarized overview, where pre-training can depend on different classes of models. One is word and context-based representations, word-to-vec, fast text, Elmo. You have simple language models. We have covered this even in the previous session with regard to recurrent neural networks, long short-term memory, bidirectional. And then we have generalized language modeling, as I was talking about, with ULM Fit, GPT, BERT, and so on. And adaptation is keep the model architecture and weights unchanged. By weights unchanged, I mean initially when you take the model, and then if you want to use it as a feature vector, you just take out the weights as features and you use it in a downstream model, like, let's say, logistic regression, or you can fine tune the entire model architecture and weights as you train it and fine tune it and adapt it to your own tasks. Let's talk about some of the fundamentals of some basic deep learning architecture blocks. The session is not about this, by the way, but this is just to give some background and context for, let's say, people who are still learning about deep learning to an extent. So one of the main constructs in any kind of deep learning model is an embedding layer. So an embedding at the end of the day is a fixed size dense vector, which is used to represent any kind of a token, in this case, words. So the idea is usually we map every word to an ordinal numeric representation based on a dictionary which we create known as a vocabulary map. And every word at the end of the day is represented as a fixed size vector. So usually it can be of size, let's say 128, 512. Common embedding size is 300 because a lot of pre-trained models like Facebook's fast text or Glove or even Google's Word2Vec is available in the size of 300 dimensional vectors, which you can download and already like directly use. That is also part of transfer learning. So word embeddings at the end of the day are basically dense numeric vector representations of each and every word. We briefly covered LSTMs, but this is just to give, again, a refresher into long short-term memory networks, which kind of try to solve that vanishing gradient problem, which we were talking about in the previous session. So one of the advantages over vanilla RNNs is LSTMs have a memory unit, so it can remember longer sequences of data. It has three main gates, typically the input gate, which decides what kind of information can be added in the current step. The forget gate decides what is relevant to retain from the previous steps and what can be forgotten from the previous steps. And the output gate decides what is the next hidden state, what it should be. And remember, over the course of multiple epochs and multiple batches going through the model and with backpropagation, these keep getting adjusted over time in the context of the output, which we are trying to predict, whether it's a sequence or a classification label, so on and so forth. And this is basically LSTM summarized in around 5 equations. So I'm not going to dive deeper into this, but feel free to refer to this. Christopher Ola's blog covers this in detail, where it talks about each of the steps with regard to, as you can see, the forget gate, the memory cell state, the tanh is being applied here. And remember, always it's matrix operations or tensor operations, and the core unit here is always a neural network where it's like a wx plus b, where b is your bias and your x is your feature and w are the weights. And these are the weights which keep getting tuned in the context of each and every equation here once there is a forward pass and a back propagation happens. And for those interested in the gated recurrent unit, it's typically a more efficient version of an LSTM, where an LSTM has three gates, as you remember, with the input gate, the output gate, and the forget gate. So GRU basically condenses it into two gates known as the reset gate and the update gate. So typically it's faster. Now, a question could be, which is a better model? Again, GRU is faster, but doesn't mean always that it is a better model. The best way is you would have to try it out on your data set. Now, the next part comes in as to the issue with sequential models. The longer the sequences are, the difficult or more difficult it becomes to capture some of the context with regard to the words. And also with longer sequences, sometimes some of the words will be related in context with the words coming later on in the sequence. So how do you code in that context with regard to words coming in later on in the sequence? Like, as you can see here, that Teddy is more related to a beer, so it's a toy, but here Teddy Roosevelt is the name of a US president. So since the word president is here, this is more contextual to really encoding the representation for the word Teddy. And this is where the bidirectional RNNs or bidirectional LSTMs came into context, where we are also going from front to back and also from back to front. In short, it is nothing complex. We are just putting two independent LSTM layers together. Input sequence is fed in forward order for one LSTM layer, and in the reverse order for the other. And at the end of the day, what happens is the outputs of these two networks, as you can see, coming out from each step. So if you consider an attention model, the hidden states will be concatenated from each of these representations and passed into a artificial neural network, like it was covered in the previous session. But if you're not using a attention layer or an attention network, what happens is the last sequence would basically come out as a concatenated representation, and it would go into the next layer. Maybe it's a dense layer or maybe a stacked LSTM, so on and so forth. And the whole idea about doing this or taking the pain to do this is to preserve information from both the past and the future to understand the context better. And this is a high level architecture again, where you can populate using pre-trained embeddings maybe. So initially we start off with an input layer, then we start off with an embedding layer where every word is represented in a fixed dimensional vector. Then we can stack some bidirectional layers. We can have an attention layer, like I said, where each state goes in, each hidden state is considered, which is fed into an artificial neural network. And then we can pass it to some dense layers if needed and do a classification in case of a classification task. And again, just a recap about attention mechanism. So like I said, instead of using the output from the last GRU cell or the last LSTM cell, you send out the entire sequence, as you can see here. You send out the entire sequence to a global attention layer. And what is this global attention layer? This is basically that artificial neural network where vectors from the hidden sequence, as you can see, HT means basically T at time step 1, 2, 3, so on and so forth. And this is fed into a learnable function. So this learnable function is the nonlinear neural net, which we're talking about. And this helps us in producing a softmax vector, which assigns weightages to each and every, you can say, the input states, right? So softmax is assigned to each and every of these input states. Though finally, when we do the matrix multiplication or the dot product in this case, we will do a dot product with each of the hidden states at every time step. So remember, this probability vector will always sum up to 1, which means that it attends to or gives emphasis to specific hidden states which are directly related to the output sequence, the current sequence which you are trying to predict. And this attention mechanism can be summarized, like I said, in typically 3 equations, where this is the nonlinearity which we are talking about, where we can use a tan h wx plus b. There are different types of attention mechanisms, as we saw, where there is a linear or a nonlinear operation which you can do. A standard one would be just a simple wx. And then you have a softmax layer where we try to normalize these weights. And then the final context vector is produced, which is then passed on to a specific sequence position in the decoder side, or this is passed on to the dense layers to do classification. So remember, this context vector is basically a weighted softmax of the hidden states at the end of the day. So this is your attention mechanism, which is just a recap again from the previous session. So now let's talk about the motivation for transformers. Before we go on to the actual transformer models, let's talk about why do we need these transformer models? What was the reason for people to come up with such a complex architecture? So this is a nice visualization where you can see that we have a sample encoder decoder architecture where the input text is here and we are passing it through the encoder. We have a context vector, and then that is input to the decoder, and out comes the sentence in the English language. So this is again without attention. So as you can see here, at every step when the input is entered, we have a hidden state which gets entered into the next RNN or LSTM cell along with the input, and then the hidden state goes on. And the final context vector is basically the hidden state which is coming out from the third RNN cell. So what happens is this entire list of, you can think of like the embeddings or the representations, all the embeddings and representations of this input. Because if you remember that this input word is first coded into an ordinal number, and then in the embedding layer, there will be a right embedding vector for this word. This will go in, and then a hidden representation is what is formed. So you can imagine that we have around 3 hidden representations here. So all of them end up being compressed into one hidden state vector, or one what is known as a context vector, which comes out of the encoder. So with longer and longer sequences, at the end of the day, we are still representing it by this fixed size context vector. And that is where, without attention, there seems to be a lot of problems when you're trying to encode longer and longer sequences. And that is where the attention models came into prominence. Because if you have a really long sequence, parts of the sequence start getting lost in terms of prominence, in terms of representation, when the final context vector comes out of this encoder side. So that is where this encoder decoder model with attention came in as a next, you can say, discovery after the initial encoder decoder model in the context of machine translation, where you take in the hidden states from each and every step. And as you are decoding every output, you consider that you consider that nonlinear transform on each and every hidden state. Instead of just taking the final hidden state vector, you consider the nonlinear transformation going through a neural network for each hidden state, compute the softmax, and then give a weightage or attend to specific sequence words or tokens which are kind of related to this output sequence. So this is where the attention model kind of tried to solve some of these issues which were there with training longer and longer sequences in the context of these encoder decoder models. And this is the attention mechanism briefly illustrated again, like I was talking about in the previous slide, where you have each of the hidden states now instead of considering only the last hidden state. And at every sequence output in the decoder, at every RNN or LSTM cell, when we are trying to decode the output, you score each and every hidden state. And how do you score each and every hidden state? So this is where you will be passing this through the neural network, the artificial neural network, and applying a tan h of, let's say, wx plus b, or wht here. Ht is the hidden state for each h1, h2, and h3. And you give a score to each and every hidden state. And then you would do a softmax transformation, like I said, to give a weightage to each and every hidden state. And then you multiply this vector, this softmax vector, the alpha, with the multiply each vector, the softmax vector, with this context vector, the context vector which you get. So this is where, as you can see here, this is the specific attention layer vector, and this is basically the decoder vector. So once you do a uh, w transpose dot v, which is v is known as a value, let's say, so w transpose dot v, then you get that final output which is coming out. And as you can see here, that these pink cells here, this is where the nonlinear transformation is happening. As I was saying, just going back again, the pink cell basically is here with this this nonlinear network, this artificial neural network. So again, coming back here, this is where each of these words, when they are being predicted finally, the attention layer is helping us to give a higher weightage to specific words which are leading to that output vector or the output sequence. Now, just to summarize the encoder-decoder models, the encoder-decoder blocks consist of multiple RNN cells. Hidden states are updated at each time step, and the vector here, also known as a context vector or the thought vector from the last step, encodes the information of the complete sequence. But if you want to build a better model, that is where attention comes into perspective, and we use a weighted sum of all the hidden states, which goes as an input to each step, remember, when we are trying to predict the output sequence, which is coming out from each decoder, RNN, or LSTM cell. So it is not just only the hidden state from the last cell, but a weighted sum of each of these will be fed into each of the decoder cells when we are predicting the output sequence at each step. So now comes the motivation for the transformer models as to why do we need these transformer models. The reasons being that encoding a long sequence without attention basically becomes a single context vector, so we lose valuable information. That is like one of the key motivations. Now, even with attention, results have shown that it is still challenging to deal with really long sequences or dependencies. And the last one, which is the most important one, is that the sequential models have limitations with parallelizing the training. What that means is you have to wait until all the time steps are gone through sequentially, and then you have to wait again till all the time steps are passed through here till you get the final output. So the training is always sequential. It is not happening in parallel, and that is one of the advantages where in the transformer model we will see that all the inputs go in, and there will be a self-attention layer where matrix or tensor operations will happen in parallel with regard to the representations for each and every word. So that is one of the main motivation of going into the transformer-based models, to parallelize this training and not wait for longer time periods to train these models. So we'll talk about transformer essentials now as to what are the essential concepts, and we'll try to unbox this transformer architecture. So briefly, the transformer architecture is very similar to the encoder-decoder model, just that it is a layered and a stacked encoder-decoder model. That's one of the key differences to start with. And it relies on self-attention and encoder-decoder attention blocks, which we will shortly see in the transformer model. And one more thing to remember here is that it's not just reliant on only one block. it has in parallel, let's say, 8 to 12 blocks, which is like known as multi-headed attention, where it tries to encode different dimensions of information into these representations for each and every word. And we'll look at this multi-headed attention concept shortly. And one of the biggest advantages is no sequential RNN or LSTM based training. It is completely parallelized. And also, as you all might already know, it has achieved state of the art performance on several natural language processing tasks. So this is again a breakdown of that encoder decoder architecture where we're talking about. At heart, as I said, the transformer model is a stacked encoder decoder model, and usually it has 6 to 12 stacked encoder decoder blocks. And as you can see, the output from the the topmost encoder will go into each of these decoder blocks, and then we'll get the final output. Usually standard transformer model architectures have 6 to 12 encoder and decoder blocks, but larger transformer models, I think we have seen even it goes up to 24 blocks or even more. So depends again on the architecture you're using. And based on the type of transformer model, so when we talk about the different categories of transformer models, we'll try to cover this, where some classes of transformer models use only the encoder block, some use only the decoder block, and some use both the blocks. So we'll see that also shortly. Let's talk about some of the fundamentals of this encoder decoder architecture. So if you break up every encoder block or every decoder block, there are a few layers inside it. One of them is known as the self-attention layer. And then you have a feed-forward neural network. So this same architecture is repeated for all the encoder blocks. And similarly for the decoder block, it has self-attention and feed-forward layers again, but there will be an encoder-decoder attention layer, which helps the decoder in focusing on relevant parts of the input sentence, which we just covered, if you remember, in the attention layer, where the attention layer will help the model to attend to specific parts of the input sentence at each time step when it was predicting the output sequence. So that is where we also have the encoder decoder attention layer, which is a new addition in the decoder block besides the self attention layer. And what is this self attention layer? So the encoder's inputs flow in through the self attention layer, and the whole idea about self attention, which we'll cover shortly, is that every word tries to attend or look at every other word in the process. So it basically tries to learn from itself as to whether some words are causing some other word, or some words are more representative with regard to some other words, or some relationships are there, so on and so forth. And the output from this is fed into the feed-forward network. And now we'll move into the next step. Again, diving a bit more deeper into this. So as you can see here, that the self-attention layer at every, so imagine this is one encoder block, and there will be 6 more or 5 more blocks on top of each other. So every word attends to or looks at every other word in this process. So we'll see shortly how this self-attention mechanism works, but just to understand on a high level, once the input representations or embeddings are present for every word, like in this case we have 2 embeddings, one for thinking and machines, it'll go through the self-attention block, and out comes 2 vector representations again, Z1 and Z2. And then this will go into each of its individual feed-forward neural networks. And by the way, this structure is replicated. So what's happening here is everything is happening in parallel, by the way. It's not like machines is waiting for thinking or something like that. Everything is happening in parallel. And outputs from each feed-forward neural network, which comes out, will be sent to the next encoder block, so on and so forth. So that is where it's not like this will process first, then this will process, and so on. So we'll talk about how sequential information is encoded in the context of transformer models towards the end of this segment. But just remember that this is all happening in parallel. So what is the self-attention? Let's try to understand it from a simplistic perspective with regard to an example, as you can see here. So if someone tells me bat, what does the word bat mean? It could mean a baseball bat or a cricket bat, or it could mean, let's say, the animal bat. Right. So in the context of this sentence, the bat was sleeping. One of the first questions is, what does bat in this sentence refer to? Now, for us, it's intuitive because we as humans have a huge knowledge base in our brain, right? So it's very easy for us to immediately understand that, okay, this is an animal. But think about it for a moment. How did you understand that the word bat is an animal? in the context of this sentence, since the word sleeping is there and was is a verb, so that is why we are inferring automatically that since the word sleeping is there, obviously a non-living thing can't be sleeping. It has to be a living thing. And what is an entity which is a living thing and a bat? It is the animal, right? It's the animal bat. So this is where to make the machine learn or to make the model learn, that is where self-attention comes into perspective, where through multiple iterations, through multiple epochs, self-attention allows the model to associate the word bat strongly with sleeping. So internally, it will have a concept that bat may be an animal, but that concept will obviously be encoded in the form of an embedding. It's not like it will be written literally somewhere as animal. So remember that this indication will be represented or coded as an embedding. So that is where, as you can see, let's say this was encoder number one. Once all the attention blocks or the attention relationships or weights are going into perspective, you can see that the word bat is slightly darker here, and you can see that this weight is slightly darker, which means that the word sleeping is related with the word bat and is contextual to it. So that is where self-attention allows the model to look at other positions or other words or tokens in the input sequence for potential clues or information which can help to better encode each word in a more contextual representation. Remember, this will not be present for things like word2vec, because when you're training word2vec, the word bat will be encoded as an average representation of, let's say, cricket bat, baseball bat, the animal bat, and so on. But here, every sentence is being passed in, and self-attention helps us to learn those contextual representations in terms of each of the other tokens. So a detailed overview now, again, trying to keep the math to a minimum, but a detailed overview with regard to self-attention. Already half an hour, but I'll try to cover this in detail. So if you remember, the input embeddings will be there for every word. That's the first step. So embeddings are generated for each word. Now there is the context of queries, keys, and values. We'll cover this slightly later also in a more detailed form so you can understand the matrix operations. But I think this was covered to an extent also in the previous session. So let's try to understand this. The first thing you need to know that query, key, and values are tensors which are trained over epochs. So these are like learnable representations. It is not a fixed hard-coded representation. Now, query usually comes in from the target sequence, and keys and values come in from the source sequence. And initially, keys and values can be same. And then it can change based on the weightages which are happening here, as you can see. And remember, I have used target and source sequences here. I haven't used encoder and decoder here. And the reason for this is if you imagine like BERT, which we'll cover shortly, BERT only trains on encoders. So then there is no concept of decoder and encoder sequences. It's the concept of the target and source sequence where it is exactly the same. And that is what self-attention is all about. It's trying to learn from each and every word in the same sequence. There is no like sequence A is coming in and sequence B is coming out. So that is why I've used a slightly different notation here as to target and source instead of using encoder and decoder. But it applies in that context also, which we'll see shortly again, where target can be a decoder sequence and the query comes in like in a traditional neural machine translation encoder decoder model, where a query will come in from a specific decoder RNN cell, and then the keys and values will be dot products. We'll compute the dot products and we'll get those alpha values, and we'll tell that which part of the input sequence is helping us predict that decoder sequence. But for self-attention, remember, target and source can be coming in from the same encoder stack. Now, the importance or alignment of every key is computed with regard to the query to get the score. So as you can see here, if I want to compute the Z1 representation, which comes in from this block, as you can see. So Z1 comes in from the self-attention block for this input. So how is this happening? Remember, all the inputs are going in parallel. So the full sentence is input to the self-attention block. And then for every token here, we are computing this score, as you can see here. And this score was the similar score which we saw when I covered this attention mechanism. Sorry for this back and forth, but just to show here, this is the same score which we are talking about. Okay, so this score is computed with regard to each and every embedding representation of the words in the input sequence. So as you can see here, the query is multiplied by the key, And remember, the key is basically the representation or the embedding representation of every word in the source sequence. Okay, so, and these are learnable functions. So initially they may be the same as this, but they may change over time. So Q1 into K1 gives us a representation, or a score rather. It gives us a score on an importance. And then these scores are divided by 8. Now, why are these divided by 8? So based on the paper, attention is all you need. You can read up more there. They talk about that if we divide by 8, it seems to stabilize the gradients. So that is one of the main reasons these scores are divided by 8. And once this is done, the softmax operation is applied. And when the softmax operation is applied, it's basically kind of scaling or normalizing the score. And remember that softmax normalizes the score and then computes the dot product of the softmax weights with the values. So the value vector is taken and a dot product is computed, and the final result vector is basically Z1, which is fed into the feed forward neural network, which you remember is above the self attention layer. So just to understand the context of these queries, keys, and values, remember that this is more in the context of language translation, again, where we are translating from, let's say, an English to a non-English language. But typically, we always start with the basic embeddings, which are generated for every word. And then we have key, query, and value tensors, where the query comes in from a target sequence. Like I said, in this case, query is coming in from the decoder sequence, and keys and values are coming in from the source sequence. So initially what happens is the query and the key representation. So what is key representations? Key representations is basically the embedding representations of the input words or the words in the input sequence. So the query and the key representations are multiplied initially using a dot product. We'll see the equation again in the next slide, I think. And once we have this matrix output, that basically gives us the alignment of the attention of every word with regard to the query. And by every word, I mean every word in the input sequence. And this is popularly visualized as an attention heat map. I think you all have seen that matrix, which was even shown in the previous session, where every word in the input sequence and the output sequence, there is a heat map which shows how closely related some of the input words are with regard to predicting every word in the output sequence. And these attention context weights from this heat map or this matrix are again multiplied with the value representation, which is the embeddings again of this source sequence, to give the outputs for the input query, which is then scaled using softmax. So just a deep dive into this again. Remember earlier we were showing for each and every sequence or each and every token here with regard to a vector, a one-dimensional vector. But this is an answer to one of the other questions also with regard to self-attention. So self-attention can be expensive, but remember that it is also highly parallelized, because we are not waiting to compute for each and every word separately. We are representing all the full sequence as a matrix representation, and we are multiplying it by a matrix representation again with regard to the embeddings or the representation for Q, K, and V. So the input sequence, if it was 2 words, it would be a matrix of 2 cross embedding size, or size of the embedding vector. If it was 10 words, it would be, let's say, 10 cross that, or 512 cross this if we padded it, let's say, with a fixed sequence length. So always remember that all these operations which we saw and which we talked about here, with the query and the key first being multiplied, a softmax is happening, and after that it's being multiplied with the value tensor. All of this is happening in terms of matrix multiplications. So that is where the parallelization is happening, and the transformers train much faster than, let's say, if it was sequential. And this gives us a representation which is directly taken from the paper. Again, these representations are lifted from a specific article, which I have linked in the references. Feel free to check it out for more detail. But just again, recapping on this Q, K, and V with regard to the self-attention. First, what happens is a matrix multiplication for the input query and the key. And key is basically, again, the input sequence. And the input query can come from the input sequence in terms of self-attention, or it can come from the output sequence in terms of the decoder. So what happens is a matrix multiplication in terms of a dot product happens between K dot key transpose, if you think about it. And once that happens, we get this representation. And this is exactly that attention heat map, which we talked about, right? Where every word attends to specific other words, and we can see these weights. So what happens next is we need to scale this, and this is where scaling happens with regard to Q, and then K transpose. So K transpose is what we just talked about. So this is basically this, if you think about it, right? There is no difference. So Q dot K transpose is here, and we divide it by the square root of dk, and this is 8 in this case, which is basically to stabilize the gradients, and we take a softmax. So basically we end up taking a softmax of this thing, and once we take a softmax of this, we have the right weights with regard to what's going to be, let's say, the context vector or the attention vector, if you may want to call it. And that is where these normalized weights are multiplied with the value vector with regard to the input sequence. And hence we get the final output, which is that Z, which we talked about previously. So this is exactly the output which is coming in from here. So again, I know this is really hard to get in just 15 minutes, but I would recommend you to check out the articles at the end of this deck also, because like for me, of course, it took several days to really understand everything, and I will still say maybe I understand 80% of it. So because there is a lot of things going on here with regard to each of the query key value vectors, and then the dot products with regard to Q and K, and finally with a V and the representation of the attention value or the vectors coming in from here. And now to the context of multi-headed attention. So far we saw that such complex tensor operations were happening with regard to the self-attention block. Now imagine 8 of those are happening in parallel, and that is exactly what multi-headed attention is all about. So this block, which we saw here, this self-attention block, imagine there are 8 of these, and every time an input is going, a different kind of representation is being encoded with regard to the inputs, the attention weights, and the outputs which are coming out. So imagine there are 8 variants of it, just like, let's say, a convolution layer or a convolution filter, if you try to think about it. When we apply, let's say, 32 filters, we are trying to learn different types of representations where one may highlight the edges more, one may highlight, let's say, the circles more, things like that. So similarly, in this context, multi-headed attention is having 8 different variants, also known as attention heads, for each of these self-attention blocks. And the input goes in, and as you can see, we split into 8 heads, we calculate the attention, and then we finally concatenate these representations and get a final vector. So this is where multiple variants of the same operation are happening. And you can ask a question here as to what's the reason for doing this? Why are we introducing this additional complexity? So the whole reason for doing this is we are trying to encode different aspects with regard to sequences, because a word may be dependent on different aspects related to some other words, and the context may be multiple. It may not just be a single context. If you see this sentence, it will become more clear. And this is a classic example of co-reference resolution, as you know. So the animal didn't cross the street because it was too tired. So the word it, we can easily understand that it's an animal. But for the machine, it's very difficult to understand it, because it may think, is it the animal? Is it street? Things like that. So that is where, if we have multiple representations or variants of this self-attention block, the attention weight vectors with regard to the values, let's say, which are coming out, they will vary. And as you can see here, this is layer 5 of, let's say, the encoder decoder stack. And these are the 8 attention heads, if you think about it, the different variants. If you look at the second attention head, the word it is gaining really high prominence from words like animal, and somewhat didn't also. Okay, so if you think about it, the word animal is really getting highlighted here and is like contextually relevant to the word it. But if you look at the third attention head, you can see that was tired. This was tired piece is also related to this word it. So that is where you can imagine that the word it here is an animal, and also it didn't cross the street because it was too tired. So different aspects or different dimensions, you can think about it, with regard to a world view of your corpus is being encoded for each and every representation. And that is why we are using multi-headed attention. So because for us, it is easy to visualize concepts in the form of different blocks or different thoughts in our mind. But how can you make a machine understand that? And that is where this multi-headed attention is trying to encode different types of concepts or dimensions with regard to each word in the context of the other words. So that is where the multi-headed attention layer comes into picture. Now we talked about transformers where everything is happening in parallel. So the next question which can come to our mind is, but what about the sequential nature of the words where, let's say, word B comes after word A, so on and so forth. So how do we encode that? And that is where positional encodings are also encoded with the regular embedding vectors for each word when we input it. So always remember that a positional encoding, as you can see here, once it's encoded with the regular embeddings, we get an embedding with a time signal. So we try to represent it in the form of an embedding itself, and we basically pass it. So even if we are parallelizing it, due to the positional nature of these embeddings being encoded into this information, the sequential representation is still maintained. Now let's talk about the decoder flow. So far, we have talked all about the encoder and the multi-headed self-attention blocks. Now, once we get the outputs, what happens? So the outputs of the top encoder, which comes out and then goes into each of the decoders, it is transformed into a set of attention vectors, basically the key and the value vectors. And then these are used by the decoder in the encoder decoder attention layer. So we talked about the decoder where there was a self-attention block, there was a feed forward block also, but in between there was a encoder decoder block. So what happens in this encoder decoder block? This encoder decoder attention layer helps the decoder to focus on specific places or specific tokens in the input sequence. And this is not surprising given it is a enhancement of the regular encoder decoder architecture. Remember one more thing, it works just like multi-headed self-attention. The difference here is earlier for every encoder block, the queries, keys, and values were basically representations of the same input sequence itself. But here, the queries matrix is created from the layer below it, and the keys and values are taken from the outputs of the encoder stack. So this is where it is slightly different, where this is coming from the layer below each. I mean, for the next decoder layer, it's coming from the layer below the decoder layer, and the keys and values matrix is coming as output from the encoder stack. And the output of each step is fed to the bottom decoder in the next time step. So the basic idea here is the inputs or the keys and values from the encoders are being fed to every decoder model, by the way. And just to quickly show this again in this representation, sorry once again for the back and forth, remember that it's not that the last encoder is only going to this decoder and we are forgetting about it. No, the keys and values are going to each and every decoder block. Remember that. So coming back to the decoder block, the outputs of each step are fed to the bottom decoder in the next time step, and then just like the encoder block, the decoders will also push their decoding results above to the each and every decoder block, just like the encoders did. And remember that we embed the and add the positional encodings just like we did before with the time step signals in the form of positional embeddings. And in the decoder layer, there is one slight difference from the encoder layer. If you remember, in the encoder layer, we passed in all the words in parallel. But in the decoder layer, we don't want, let's say, the later words to be known by the previous words, because we don't want it to know that context beforehand, right, as to which word is coming in later, because that would kind of be, let's say, like cheating. So to prevent that, what happens is the self-attention layer is allowed to attend to earlier positions in the output sequence. And that is basically done using a masking layer where we put a mask in the form of -infinity or something like that for all the other words, the future words in the sequence. So in this case, let's say A would be masked, so on and so forth, when it's being inputted. And the final layer in the transformer model is basically where we have this decoder stacked output, and it goes through like a regular feed forward neural network. We get the logits, we do a softmax, get the probabilities, use an argmax to get what is the most probable word which we are trying to predict. So now let's talk about the transformer model architectures. Already it's 45 minutes. So this should give you a good idea about what are the different types of transformers out there, because a lot of us think that transformer means bird, but that is not the case. So there are different types or classes of transformer models. One of them is autoregressive models. So for autoregressive models, we only consider the decoder of the transformer model. and a mask is used on top of the full sentence. So like I said, the attention heads can only see the previous words. We don't see the next words. That is what is done in the decoder block. And the classic task for these is text generation. So it's pre-trained on a language modeling task of guessing the next word given the previous words. And the most popular family of autoregressive models is the GPT models, GPT-2 and now GPT-3. Auto-encoding models. So this is basically the BERT family of models, and they only use the encoder part of the transformer architecture. If you remember encoder and decoder, so decoder is used by GPT models, autoregressive models, and encoder is used by the auto-encoding models. So this is where they get access to all the inputs without any mask. But for one of the tasks, which we will see shortly in the BERT model, which is known as masked language modeling, where we do the pre-training by corrupting inputs tokens in some way, by basically masking them. And we try to guess those tokens and try to reconstruct the original sentence. And like I said, BERT, Albert, Distal BERT, all of these are auto-encoding models. The next one kind of uses a combination of both. That's why it's a sequence to sequence transformer model, which, as the name mentions, it uses both the encoder block as well as the decoder block. And popular applications include neural machine translation, summarization, question answering, so on and so forth. Popular models are BART from Facebook, text to text transformer, I think T5. This also I think came out recently. And the last one is multimodal models. Again, I haven't really dived too much deep into this, but this is where it tries to make state of different modalities like text, images, and so on, and try to use that in the context of any kind of downstream tasks. So popular transformer models, considering an autoregressive model, it's, let's say, like a GPT family of models, which uses only the decoders, and considering an auto-encoding models, it's basically the BERT family of models, which uses only the encoder blocks. So let's understand BERT and distal BERT because we'll be using shortly in the hands-on. BERT is basically a trained transformer encoder stack. As the name suggests, bidirectional encoder representations from transformers. That's the full form of BERT. So remember, encoder representations from transformers, it means only use the encoders blocks in the encoder block in the transformer model. So the BERT training workflow is basically twofold. The first one is the pre-training, and the next one is the fine-tuning, if you remember pre-training and adaptation. So the pre-training is also known as a semi-supervised learning or semi-supervised training, where we take in large amounts of text data in the form of books, Wikipedia, so on and so forth. And we basically have two tasks here. One is the masked language modeling task, and the other one is the next sentence prediction task. So these two are run to train this BERT model so that all the representations are being learned in this model with regard to the context of all the corpus text which is being fed to the model. And once this transformer model is ready in the form of a pre-trained model, that is where we fine tune it in terms of a supervised learning step. Let's say if we were building like a classification model, which we will see in the hands-on. So BERT training workflow, one of the main tasks is masked language modeling, where we have an input sequence. And as you can see, we corrupt this input sequence, and we corrupt this by masking out some of these words as we input it. And then we try to predict, okay, what are these words which could be present in the context of all these words which are occurring around it. So this is where this task is known as the masked language modeling. Use the output of the masked words position to obviously predict that masked word. Next sentence prediction. So this is where we have two sentences in sequence, as you can see here, with a separator. And we try to say that whether this sequence should come after this sequence, whether it is next or it is not next. So this is the next sentence prediction task. And these two are the main tasks which are a part of the pre-training workflow of BERT. Now imagine we have done this already, or Google has done this for you, and you can download a model directly from TensorFlow Hub or somewhere else. That is where you can now fine-tune BERT in basically solving what's known as a multitask natural language processing in terms of sentiment analysis, classification, sentence tagging like named entity recognition, question answering, so on and so forth. So this is where you can use BERT in different formats to potentially solve your own task, and that is known as the adaptation phase of using a transformer model. So for text classification, it is pretty simple. We need to encode our input sequence in this format where we have the token embeddings, we have the positional embeddings and the segment embeddings. For classification, this red block indicates that there is no concept of next sentence prediction. So we just will input one sequence, which is encoded with a CLS and a SCP token. And this input sequence will go here, and we will fine tune this neural network model or this transformer model in the context of doing text classification. So this is the adaptation phase where we fine tune our transformer model. A brief into the challenges with this massive size of the pre-trained model. So as you can see that more complex the model, more the number of layers, the memory footprint of this really increases. And as some of you who have already maybe trained transformer models, you know that even fine tuning them can be a huge pain with regard to batch size, sequence size, even when you're using a powerful GPU. And that is where DistilBERT was released sometime back by Hugging Face, I think probably in the last year, where it has really reduced the memory footprint with regard to the total number of parameters, I think 66 million or something like that. And this is where it's known as compressing BERT. So it has used something called knowledge distillation to compress the total number of parameters. In more particular, it's known as teacher-student training, where we have a teacher model, which is, let's say, the BERT model, and we take in the output distributions with regard to that model, and we use that as input representations to train what is known as a student model. And this is where it is trained in using cross entropy on soft targets, which is the probabilities from the teacher model, not the actual class representations. And the loss it uses is the KL divergence loss, because it is working on distributions, if you remember, not discrete values. And again, do dive deeper into it in this article if you want to, but looks like they have almost half the number of parameters from BERT and retained like almost 95% of the performance. So this is where DistilBERT or models using this compression technique are becoming more and more favorable, where we can sacrifice a bit of the accuracy, but it's much faster to train. Its memory footprint is lower, and maintaining it, deploying it also can be less a challenge, let's say, versus using a huge model like whatever Transformer XL or BERT itself, BERT large, let's say. So finally, we are done with all the concepts. Hopefully this was useful. We'll go into the hands-on tutorial now. These are the tutorials we'll be covering now. One is text classification with a less data problem. We'll look at how logistic regression performs on a benchmark sentiment classification data set. And then we'll look at how BERT and DistilBERT can be used and trained on. And then we'll look at an interesting aspect of transformer pipelines from Hugging Face, where you can easily solve multitask NLP problems. And we will look at how you can easily solve these using pre-trained models right out of the box with regard to named entity recognition, Q&A, chatbots, text generation, summarization, translation, generation, feature extraction, lots of stuff. So I'll try to cover this in the next 15 to 20 minutes. I know I'm already running out of time, but that's the nature of this topic. Let's quickly go on to the presentation. Let's see. So again, for those of you who want to use this in the future, the notebooks are in this repository. I will again type in the link for people to see. So this is the link. I'll just wait for a few seconds in case someone wants to, in case someone doesn't have it who joined in late. So bit.ly transformers_ds. That is the link. This will redirect you to the GitHub repository with all the examples. Okay. Now going into, there are two notebooks here, as you can see. So we'll open this up with Colab, and these notebooks have been self-contained, which means you can directly upload it to Colab. It has all the dependency installations already in the notebook embedded, so you can directly run it without worrying about what I need to install, so on and so forth. Let's move into the first hands-on. So deep learning with transformers, we look at BERT and DistilBERT. We are not using fast text here, by the way, but we are only using transformers and the TensorFlow TF2.x. but it can easily be adapted to PyTorch. I'll say which part you just need to change maybe. So basic dependencies using the transformers library, importing the necessary dependencies here, uh, TensorFlow version. It's using the GPU as you can see. So remember, if you want to run this to change your runtime backend to GPU, if you're running it on Google Colab. So we'll be using the IMDb large movie reviews dataset. It's a standard one I use for most of my tutorials, and you can also check it out anytime. The Stanford URL is here if you want to download it, but I already have it in a repository. So basically 50,000 labeled IMDb movie reviews, where sentiment one means the movie review was having a positive sentiment, and otherwise the movie review was having a negative sentiment if it's zero. Simple binary classification problem. Now, let's simulate this in the context of a small data set problem. So for our training, we will train on only 5,000 reviews, as you can see here. For validation, when we validate across the epochs in the deep neural network, we will use, again, 5,000 reviews to check our performance across every epoch. And the last one is the test data set, where we will actually test on the last 15,000 reviews. Again, this is just as a representation. Feel free to use like train test split and other ways of splitting the data if you want. This is just for ease of use. That's it. Now, our train reviews are in this format. As you can see, 5,000 training reviews, 5,000 validation, and 15,000 test reviews. So in this case, our test data is more than our training data. You can see almost 3 times. Now, let's start with a standard machine learning model where we first build a logistic regression model on the first 35,000 reviews, and we will test on the last 15,000 reviews, let's say. And then we will build that same logistic regression model with only 5,000 training data, and we will see how does the performance change. And then we'll move on to BERT so that you understand the concept as well as the reason as to how small data problems can affect the model performance. So some basic text pre-processing, again, I won't cover this in too much detail, but what we are doing is removing any HTML characters, converting any accented characters, fixing contractions like won't to would not, and removing some special characters like symbols and so on. Remember, for BERT, we won't be using any of this pre-processing, and that is the best part of it, where you can directly pass this data into BERT. We are doing this for the logistic regression piece. So stripping HTML text, you can refer to this code later. It's there in my repository, but standard code for removing HTML text, removing new lines, extra tabs, spaces, and so on, fixing the contractions, removing accented characters, lowercasing, removing any extra spaces, stripping the string. Once we have this, data is pre-processed. So let's talk about the first machine learning model, which is the logistic regression model. So this is where we do a simple count vectorizer, a bag of words model. And as you can see, we are training it on 35,000 input training reviews. And we are trying to predict the performance of the model on 15,000 test reviews. And after applying the bag of words feature vectorization method, we can see that we have a total of around 52,000 odd features, which is pretty huge, the dimensionality. So once we build a logistic regression model on the training features and we get the prediction on the test data, we can see we reach a 89% accuracy, F1 score, whatever be it, on our test data of 15,000 reviews, which is pretty decent. And again, this data set is a benchmark data set. So it's not that difficult to get above 80% accuracy on this. Now let's switch the context. Imagine we had only 15,000 reviews and, imagine we had only 5,000 reviews this time for training, as you can see. So training data is only on 5,000 reviews now, and we want to predict on 15,000 reviews. So we build our feature vectorization only on the training data vocabulary with the fit transform, and then we are transforming the test data so that the vocabulary remains fixed only on the training data context, though 5,000 reviews. So you can see now the feature space is almost halved. So obviously we are losing a lot of words because obviously we don't have that data. So now once we train this model, you can see that the accuracy, though it's still good because it's a benchmark data set, it's dropped by almost 4 to 5% from before. So that's the problem with small data or insufficient data. When we have less data, it becomes really difficult when you're building a model from scratch. So now let's talk about the whole aspect of transfer learning where we use this pre-trained BERT model. So this is where we will need to first tokenize using BERT. So I'm using the BERT tokenizer here, and I'm using the BERT-based uncased model. Just a brief, BERT uses a word piece tokenizer based on byte pair encodings, where if there is a bigger word, which is, let's say, uncommon, it will break it into subwords, similar to the concept of fast text. I'm not going this into too much detail due to the interest of time, but you can find the details here with regard to the word piece tokenizer, which is slightly different from a normal tokenizer, let's say we use from Spacey and so on. So we lowercase our text, we tokenize it, break it into word pieces using this tokenizer from Hugging Face, the word piece tokenizer. And then we add a special CLS and SAP tokens, and we append the mask and the segment, just like we discussed in the BERT paper, where you need to have a mask if you are planning to mask your tokens or corrupt the tokens. In our case, we are not planning to do it. So you can see that for every, let me just walk through this briefly. We first tokenize this to get our tokens for each and every word, token representations. We wrap it with the CLS and SAP tokens, the beginning and the end. For us, we are putting one for the mask, which means basically we don't want to do any masking because we don't want to corrupt any tokens. So basically, that is what we are planning to do, I think. Sorry, that is a dimensionality. That's why I had the doubt. So one obviously means a true in Boolean terms and zero means a false. So here we are creating a mask vector, which is the same length as our token vector of all the words in the sequence. So initially the mask is all ones. And what we are doing is for all the tokens till we are reaching the end of the sequence, we are putting a zero basically. So what that means is I am basically telling that don't mask anything. That is what I'm trying to do. And also if you see segments, we are setting it as zero, which means I am basically telling it that there is no notion of a segment concept in this BERT model input. So if you remember, segment is used in that next sentence prediction. If we have two sentences, the first sentence, all the segment IDs would be zero, and the next sentence, all the segment IDs would be one. But in this case, I'm dealing with only one sentence, if you remember from that slide. So just to go here quickly to clear this concept once again, we only care about this part. We don't care about this part. So that is where, since we are only concerned with one sequence here, that is exactly why we are using the segment IDs of only zero. We don't care about the segment IDs of one. Now, moving on, we build a model architecture here. So if you remember, the outputs here is the IDs for every word, the masks and the segments. And this is the input the BERT model expects in terms of when you are trying to feed in the input to the model. So we have the input ID, the mask, the segment IDs. You pass it or you create a tensor from this. That is your inputs. I have set the max sequence length to 500. Obvious reasons are the limitations of the GPU in Colab. Now I'm using here transformers TF BERT model from pre-trained. So this is my BERT model, the pre-trained BERT model, which I'm using. For people who are using PyTorch, you can just remove this TF part and you will end up using the PyTorch variant of the model. Just something for PyTorch enthusiasts. And now once I have the pooled output, which is the hidden state, basically that is a dimensional vector of size, as you can see, 768. So this 768 size vector is extracted out here. And then I'm passing it to dense neural network here with two dense layers. Again, you can play around with dense layers here, putting some regular dropout. The last dense layer is one because obviously it's a sigmoid activation, right? Simple logistic where we are predicting either a one or a zero. We set a low learning rate here because we are trying to fine tune the full BERT model, all the weights, if you remember, so we don't want to mess things up. And this is the architecture of the model where the three inputs are being fed into the pre-trained BERT model, extracting out the hidden state from the BERT model, the 768 sized vector, and then passing it through two dense layers. So that is what we are doing here. So converting the documents to input features, this is where we are creating those three vector representations with regard to the input IDs, the masks, and the segment IDs for the training data and the validation data, as you can see here. And then we are basically building our model, where we pass in the inputs, ID, mask, and segment IDs, pass in the corresponding sentiments. For validation data, again, we pass in the same formatted data, as you can see. And we use early stopping. In that way, you can give 100 epochs also, but if your validation loss is not increasing, in this case, we use a patience of 1, which means in the next epoch, if your validation loss has worsened, then stop the model training immediately and restore the last best model. And that is exactly we do here. And you can see the training time is pretty big. I mean, even if it's training on only 5,000 records, it takes 822 seconds to train one full epoch. And you can see in the first epoch itself, we get a huge boost in the validation accuracy, which seems interesting. So now is the time to test on the 15,000 records of test data. And as you can see, we convert it into the same format again, the test input IDs, the token IDs, the mask IDs, and the segment IDs. And we pass that as an input into our fine-tuned transformer model. So now we are predicting on this test data, and we do a simple 1 or 0 prediction based on the prediction probability. And as you can see, our score is pretty good. We have trained on only 5,000 records, if you remember from before. We trained on only 5,000 records. But we are predicting on 15,000 records now, and our score is 92%, which is really good. So if you actually trained on 35,000 records, you would see it would boost up to 94 or 95%. So that's the power of transfer learning in the context of transformers, where you have so much data that it becomes where you don't have so much data, that even if there is a lack of data, if you use models like this, usually you may end up with a good performance. But again, depends on the context of your data, so on and so forth. It is not like this is a silver bullet to everything. I'll just highlight briefly the difference in the Distilbert model. I won't go into too much detail due to the interest of time, and we have to cover one more notebook. So for Distilbert, the only change is Distilbert tokenizer and pulling in the Distilbert model. It again uses a word piece tokenizer, by the way, there is no difference. And now you create these inputs with the same CLS and the SCP tokens. The only difference here is Distilbert was not trained on this next sentence prediction aspect. So there is no concept of a segment ID here. There is only the concept of the word ID themselves and the mask, whether it's a 1 or a 0. So in this case, we obviously will unmask everything because we are not doing the pre-trained part of BERT, no mask language modeling. We are predicting, fine-tuning, classifying. So only care about the IDs and the mask. There is no segment IDs. That is the only difference from the BERT model and the Distilbert model. Again, exactly the same architecture with regard to extracting out the hidden states in the pooled output. Model we are using is TF Distilbert model from pre-trained. So that is the model class we are using from the transformers package. If you are using PyTorch, you can use Distilbert model directly. No need to prepend the TF. And as you can see, input here is only the input IDs and the input masks, no segment IDs. I wanted to reiterate that again. Again, similar learning rates and so on, converting the features and then building the model. You can see we reach around 90% validation accuracy. Check the performance in the same way using only the ID and the mask IDs, word ID and the mask IDs. And you can see that we reach a 91% F1 score, which is kind of a little bit less obviously than BERT, but pretty good and much, much more than that logistic regression model, which we trained initially. So hopefully this gives you a good context of solving problems with small data also, where you can fine tune a transformer model in this way by using the right input. More than often, the biggest task here often with these kind of models is shaping your input in the right way. As long as you can do that, as long as you can encode in the right representations, as you can see, calling the model, this is not rocket science, it's just one line because Hugging Face has made it so easy to use these APIs. Okay, last notebook. I hope to cover this in hopefully 5 to 6 minutes. I'm already well beyond time. Thanks for staying so late. So for multitask transformers, we will see how we can use this pipeline framework and we can solve various tasks. So transformers has introduced a pipeline framework. The way to use this API is pretty simple. You pass in the task name which you want to perform with regard to the pipeline construct. You can even pass a model name as optional arguments. Otherwise, it'll use a default model. And then you basically use it for the task you want to do. So installing transformers, from transformers, importing the pipeline module. Now, first thing we want to do is sentiment analysis. There is already a pre-trained model, just like BERT. I think by default it uses BERT, which is trained on the sentiment analysis task. So all you need to do is call pipeline of sentiment analysis, and you can see that it is downloading a lot of things. So these are the model weights, model architecture, so on and so forth. And then you can directly call this on any text data. And as you can see that it is even able to handle things like negation. So that's where you can use a sentiment analysis model right out of the box, and this may give you a better performance than, let's say, text blob or something, which is a lexical model based on only a dictionary, not so much on context. Right, a lot of you must be knowing about text blobs. So this is where you can use this model directly for sentiment analysis, especially, let's say, when you don't have label data, and you can easily use this. Next one is named entity recognition. You just call pipeline of NER. You get the relevant models. You can see it's a huge model. It has downloaded almost 1.3 gigs. So be careful about your about your usage of data when you're using these models. Now we have this huge text. We want to extract the entities. So you just call the pipeline object of NER on this text, and you can see it has identified the entities. Facebook is an IORG is organization. It uses the word piece tokenizer, if you remember, which breaks uncommon words into multiple pieces. So you can see that this part, let me zoom this a bit. Yeah, this part, Mark Zuckerberg. So you remember it breaks it up into subwords. So this whole entity is represented as a person. So basically this means Mark Zuckerberg is a person entity. And then you can see Brazil location, Latvia location, Singapore location. Won't go into too much more detail, but you get a well-trained NER model right out of the box without doing any kind of fine-tuning or training using things like conditional random fields and so on. Okay, question answering. So just call pipeline of question answering. This is an interesting application I had shown some time back, where let's say this COVID situation is going on and there is this whole aspect of fake news and so on. So let's say you have some context data or data from a index or a database where you have some factual information about the recent coronavirus, COVID-19. And then you can build kind of a chatbot on top of that, where you pass in the relevant database context, the data context, and you ask a question: what is a coronavirus? And you can see it's trying to extract relevant pieces from that information. And we didn't really need to fine tune it here, but if you wanted to fine tune, you would need to format your data in the squad format and then fine tune the model. But you can see what is a coronavirus, large family of viruses which may cause illnesses in animals or humans. What is COVID-19, most recently discovered coronavirus? Remember, coronavirus is a general entity. There are many types. So COVID-19 is the most recent one. What are COVID-19 symptoms? Fever, dry cough, tiredness. How does it spread? Small droplets from nose or mouth. How do people get infected? By touching these objects or surfaces, then touching their eyes, nose, or mouth. How can we protect ourselves? Practicing hand and respiratory hygiene. I think that is pretty intuitive for us, but you get the point, where this is the power of pre-trained models and pre-trained transformers, where you can leverage it for a wide variety of tasks now with minimal code, thanks to these really nice interface application programming interfaces. Mask filling is more about next word prediction, where like the ship is reaching the surface, port, shore. These are different options, like a next word prediction. Summarization is interesting. So BART, like I said, is a model from Facebook, which you can use for summarizing text data. Remember, it's a sequence to sequence transformer model. So you have this huge block of text here. I want to summarize it, just call summarizer on this big doc here. And you can see here, COVID-19, most infectious disease caused by recent coronavirus pandemic affecting countries globally, kind of summarizes the whole information related to the recent COVID-19 text which we had. Translation, again, this is still being built, but you have the common ones here, like English to French, English to, I think, Deutschland, that's German, and so on. text generation also, you can use a GPT model directly just like this and start generating text, where I passed it an initial sequence, today is going to be, and it automatically starts generating text for you. So you can automatically generate text here. And I was talking about using BERT with logistic regression. So that is where we can pass in an input sentence. We call the pipeline for feature extraction. And as you can see, for this whole sequence, we get this feature vectors. And then we can use these feature vectors and do an average or something like that for every sequence, and then pass it into a machine learning model if you want to, or do some cosine similarity analysis, so on and so forth. Okay. So that brings us to the end of the demo. I'm over 20 minutes, but these are the references of what I've used. I've referred to a lot of research papers, and most of them I've put in this GitHub repository itself here. Feel free to check it out. And obviously, I didn't invent all of these content. Thanks to all of these folks for providing a lot of nice videos, visuals, as well as some concepts, which I could kind of summarize, let's say, last 3 years worth of research into this 1 hour session. So yep, that's it. Hopefully this was helpful to an extent. These are my links if you want to connect with me. Thanks a lot. So open for any specific questions. If we have them, Usha, if you're there.
Yeah, I'm there. I'll read out a question.
Maybe
This
maybe
is
we can take 2 or 3, and you can reach out to me offline since I'm already over time.
yeah, yeah. So BERT has 512s length. How can we use it for longer multiple sentence? Say I have 1,000 words in my input.
Check out Transformer Excel or the long former. I haven't used it, by the way, but that is where it seems you can use longer and longer sequences to potentially train a model. Again, this is based on what I've just read. I haven't implemented it myself, because for our case, after 512, there will be a memory issue, even if I want to use 1,000. So it depends on two things. One is the type of model you're using. Check out long former or Transformer Excel, and also make sure you have good enough GPU infrastructure.
Yeah. So this is from Shilpa. What is BERT sentence transformer? Is it the same as BERT tokenizer? How are they different in usage?
BERT, okay, so BERT, I don't know what you mean by sentence
BERT
transformer.
sentence.
Maybe someone has built a new thing, but based on sentences. But BERT has two aspects. One is the tokenizer, which uses the word piece tokenizer to tokenize and represent each token, if you remember, in terms of the ID, the mask, and the segment IDs. And the transformer is the encoder block, as we talked about, which is used for the actual modeling.
So there is two more questions. Yeah, from Utaksh, how can we create a good context vector if the input is a sequence of events, example, clicks of customer, where the time between clicks is also important and should be used in the input as well?
Two ways. One is you can use an attention model where you have your inputs, and over time you're trying to potentially pass it through that attention layer, if you remember, where at each output sequence we are trying to refer to which parts of the input sequence are important and should be attended to. The other way, which is an innovative way, is use a kind of a CNN approach where you can bucketize your time intervals or something like that. All your events are your y-axis, and you can put some frequencies. So you get the point. Have like a event heat map over time, and if you build these feature maps based on various time intervals, you can even use it for predictive analytics by passing it through a CNN. So that's another innovative way of doing it.
There's one question by Chaitali. So BERT must, so the auto encoders can actually learn the context like RICAP in Vision.
Mm-hmm.
So this is what she asked. I mean, is it a question or she's just confirming it with you about
Yeah,
something?
I mean, yeah, autoencoders can learn the representation with regard to an image. Similarly, here, basically, whether it's the encoder block or the decoder block, we are trying to similarly learn representations with regard to the text data. Yeah.
So Anish sent a question. Is there a way to give custom attention weights to some words? Example, medical terms, etc. Is it possible to give custom attention weights?
So the attention layer is a neural network. If you remember, I talked about it before, the artificial neural net, feed forward neural network. So therein you can't give it, obviously, but if you can weigh the words maybe in terms of somehow weighing their embedding representation or the word by itself, then maybe it is possible. I haven't really tried it though, but in the basic attention layer implementation, I don't think so, unless let's say you are able to figure out somehow using the mapping that okay, if sequence is a1 a2 a3 a4 and a2 and a4 should be highly weighted, then after the softmax or before the softmax you can introduce some more weights, but you would need to know at which position in that hidden state sequence vector those words are occurring. So you would need to do some custom coding. I guess it is possible, but you can't like modify the attention neural network layer. Yeah, but you can do it after that.
Yeah. There's a last question. This is from Suesh. Is there any use case related where question that is not answers, question can be generated from sample text be achieved using transformer implementation?
Yes, yes, I think so. Someone had done this a while back. I don't remember who, but there was an article on this. It's called paraphrasing. So you can take this Quora question pairs data set. It's available on Kaggle. So it has basically whether a question is a duplicate of another question, right? That kind of thing. And if you train or fine tune a BERT model on this or a transformer model on this, then it's called as a paraphrasing task, where if you pass in a sequence as a question, it will generate similar questions to you. I think it is possible. Yes.
Yeah.
Check out based on that. I think there'll be some article on that. Yeah.
So we've taken answered all the questions in
Yeah.
the comment section, and if there is any question which you is not answered, and you can always reach out to Dipanjan and LinkedIn,
Yep.
Twitter, and Medium, GitHub. Yeah.
Yeah. Sorry,
Thanks
I
a
don't use
lot.
Twitter, but
Oh,
yeah.
okay, yeah, okay. LinkedIn, GitHub, and Medium. So yeah, thanks a lot for the
Yep.
amazing session, Dipanjan. There's a lot of
Sure.
great comments out there in the comment section. Hope you get some time to read that.
Sure.
And
Thanks
yeah,
everyone for staying almost half an hour late. I really appreciate it.
so this is a session where we had the highest record number of audience, where we had more than 85 people at peak time watching
Nice.
live. So we're very happy about that. And also Vimalji as Mysuru, thanks a lot to the audience as well for joining us on Sunday night. And Vimalji as Mysuru is going so big. We just started our events in February, and in just 3-4 months, we are 1,700 members strong, and we're looking for volunteers to expand our team. So if you're interested to be part of core team of MLGS Mysuru, please you can reach out to me on Twitter at urangaraju. And yeah, looking forward to the session next week. The next couple of weeks we have already have sessions in the meetup page. Go check out for it. And thank you everyone, and thanks Dipanjan, and I'm ending the
Yeah.
broadcast now.
Thanks a
Yeah,
lot, everyone. Yep.
yeah, thanks a lot.